Captions in English, please. So this is the 7th video of chapter 8. It's on empirical formula from experimental data. So up to now, you've been used to seeing molecular formulas. But can we calculate a chemical formula from a mass percent composition? Yes, but it is the empirical formula, not the molecular formula. So what is the empirical formula? The empirical formula only gives the smallest whole number ratio of each type of atom in a compound, not the specific number of each type of atom in a molecule. So molecules can be made of several of each of the atoms, but the empirical formula will only give you the smallest possible whole number ratio for each type of atom. And so the molecular formula, what you're used to, is always a whole number, a multiple of the empirical formula. For example, the molecular formula of hydrogen peroxide is H2O2, and its empirical formula is HO, because you can bring it down to just one H, one O. That's the ratio between the atoms of hydrogen and the atom of oxygen. There is one oxygen for one hydrogen, but the real molecule is made of two oxygen atoms and two hydrogen atoms bonded together. So let's go through this concept check to make sure you understand what is the empirical formula. So we have these molecular formulas, and we want to find the empirical formulas of these. So glucose, C6H12O6. To find its empirical formula, you want to divide all the subscript by the same number, and usually you use the smallest subscript. And here the smallest subscript is 6. So dividing 6 by 6 is going to be 1, 12 by 6 is going to be 2, and 6 by 6 is going to be 1. So the empirical formula for glucose is CH2O. So the molecule has one carbon for one oxygen and two hydrogens. Butane, C4H10. Here, if you divide by the smallest subscript of 4, the problem is that 10 divided by 4 will be equal to 2.5, and that's not a whole number. So we cannot divide by 4. So we have to find a common multiple here, and that's going to be 2. If you divide both subscripts by 2, you get this C2H5. So you have 2 carbons for 5 hydrogens in this molecule of butane. Dinitrogen tetroxide, N2O4. Here you can divide both subscripts by 2, and it's going to be NO2. 2 divided by 2 is 1, and 4 divided by 2 is 2. And nitrogen dioxide, NO2. Here you can see that dividing 1 by 1 stays a 1, and 2 by 1 stays a 2. There's no way to make this more simpler. And so the empirical formula is the same as the molecular formula in this case, NO2. So we can find the empirical formula from experimental data. Let's say you're doing an experiment like a decomposition of water. If we decompose a sample of water in the laboratory and find that it produces 3 grams of hydrogen and 24 grams of oxygen, can we retrieve the empirical formula? How do we determine it from these data? So you see that the masses here are not helpful because the mass of each atom is different. So you cannot use that to have proportions. So the steps to obtain an empirical formula from the experimental data is first, you write down or calculate the masses of each element present in a sample of the compound. For example, we were given the 3 grams of hydrogen and 24 grams of oxygen. But sometimes you can be given the mass percent composition only. And so for this, you will assume you have a 100 gram sample of the compound. And then you will calculate the masses of each element from the given percentages. So you transform the percentages into masses in grams for 100 grams of the whole compound. Once you have the masses of your elements of each element, you will convert them to moles, number of moles, by using the appropriate molar mass for each element as a conversion factor. So the molar masses, you find them in the periodic table for each element. Once you have the number of moles for each element, you write a pseudo formula for the compound using the moles of each element, as subscripts. And then you divide all subscripts of the formula by the smallest subscript. If after dividing by the smallest number of moles, the subscripts are not whole numbers, then you multiply all the subscripts by a small whole number to arrive at a whole number subscripts. For example, if your subscripts are a fractional subscript in 0.10, then you would multiply all the subscript by 10 to get rid of that 0.10. If the fractional subscript ends in 0.20, we would multiply all subscript by 5. If it's a fractional subscript in 0.5, you would multiply all subscripts by 4. If it ends in 0.33, you would multiply by 3. If it ends in 0.50, you would multiply by 2. If it ends in 0.66, you would multiply by 3. And if it ends in 0.75, you would multiply by 4. So this is to get rid of the decimal part and have only whole number of subscripts, but the smallest possibles that you can arrive at. So let's go through this example that we started with the decomposition of water that gives 3 grams of hydrogen and 24 grams of oxygen. So we have our masses. So we need to determine now how many moles of each element was formed during the decomposition of water. So we take the masses that are given and we use the molar mass to convert that to moles. So the molar mass will be written as a conversion factor with the grams on the bottom and the mole on top so that we can cancel the grams of hydrogen in this case. So the molar mass of hydrogen is 1.01 grams per mole. And so that gives the same number of moles actually here, 3 moles. And then you do the same with the mass of oxygen. So 24 grams of oxygen, multiplied by 1 mole of oxygen over 16.00 grams of oxygen. That's the molar mass of oxygen, 16 grams of oxygen per atom of oxygen, per mole of atoms of oxygen. So 24 divided by 16, that's 1.5 moles. Here, notice how we don't use O2 or H2, even though when you're decomposing water, that's what you're forming. You're forming the diatomic molecules, oxygen gas and hydrogen gas. But we are looking for the ratios of the elements, hydrogen and oxygen, so just single atoms here. So that's why you use the molar mass of a single atom, of single element, I mean. So here there are 3 moles of hydrogen for every 1.5 moles of oxygen in this molecule. So the next step is to write the pseudo formula for the compound based on the moles of each element. And so here we have 3 moles of hydrogen and 1.5 moles of oxygen. So you use those numbers as subscript. And so that pseudo formula would look like this, H3O 1.5. And so to get rid of the 0.5 here, you want to divide all the subscript by the smallest subscript, here the 1.5. So we would take the 3 divided by 1.5 and the 1.5 divided by 1.5. And so the formula becomes H2 because 3 divided by 1.5 is 2. And then 1 oxygen. And so the ones are always implied in the formulas, so it's becoming H2O. So that would be the empirical formula for water, H2O. And so you know that it's also the molecular formula in the case of water. And that makes sense because when you have only one atom of one element, there's, typically the molecular formula will be the same as the empirical formula because you cannot simplify that more. And the molecule of water is really made of just one atom of oxygen and two atoms of hydrogens. So let's go through an example here that shows how we can calculate the empirical formula from the mass percent composition. So we have this other example, mercury and chlorine combine to form a compound that is 73.9% mercury and 26.1% chlorine by mass. If you add those two percentages, it gets to 100. Determine the empirical formula for the compound. So here you're not given masses per se, you're given percentages of mass percent composition. So here what you have to do is you assume that you have a 100 gram sample of the compound. So if your compound, you have 100 grams of it, then you take the percentages of mercury as the mass of mercury. So the 73.9% of mercury will be changed into a mass of mercury. And then the 26.1% of chlorine will become 26.1 grams of chlorine. And the total is 100. So you suppose your sample is made of 100 grams of the compound. So then we have masses now that we can change into moles. And for this, you will use the molar mass of each element. So let's start with mercury. 73.9 grams of mercury. You multiply by 1 mole of mercury over 200.59 grams of mercury. You have the grams on the bottom of the conversion factor because you want to cancel grams of mercury. In the calculator, you do 73.9 divided by 200.59. And the calculator answer is 0.368413. But here the percentages they were given with 3 sig figs, so we keep 3 sig figs. So 0.368 moles of mercury. Next, you do chlorine, 26.1 grams of chlorine multiplied by 1 mole of chlorine over 35.45 grams of chlorine that you find in the periodic table. That's the molar mass of chlorine. So we have the grams on the bottom, so we can cancel grams of chlorine. In the calculator, you do 26.1 divided by 35.45. And the calculator answer is 0.736248, etc. But we keep 3 sig figs like in the given mass. So 0.736 moles of chlorine. Next, you write the formula starting with mercury and finishing with chlorine. Always metal first, non-metal second. And you give the subscript, you give those number of moles as subscript. So Hg 0.368 and then chlorine 0.736. And you use that now to find the empirical formula. So you divide both subscript by the smallest one. So here the smallest one is 0.368. So you divide both subscript by 0.368. And so for mercury, it's going to be a subscript of 1. And for chlorine, it's 2. So it's going to be HgCl2. That's the empirical formula for mercury 2 chloride. And that would be also the molecular formula in this case, because here mercury will be a 2+ ion and the chloride are -1. So this is a neutral formula. And that's the molecular formula for mercury 2 chloride and the empirical formula.